So I want to start by making a small apology. I am doing this talk from an airport, and so it's possible that we may be interrupted by announcements from the, like that, for example. But they haven't been happening very often, so I'm hoping it won't be too disruptive. So as Ilya just mentioned, I want to start my talk by giving the floor for a couple of minutes to an absolute hero of this field, Didier Clenel, who has been a substantial supporter of my various foundations for many years, and who at the moment is funding a challenge grant to LEV Foundation, which officially ends tomorrow. He has put up, really a substantial proportion of his own net worth to support the work that we do, which I'll be telling you about in a moment. And he has done it as a matching challenge. So anything that anyone else gives by the end of tomorrow will be doubled by Didier. So I will let him have the floor for a couple of minutes.
Yes, so really a few seconds. We see objects extraordinarily small. We see objects extraordinarily distant. We benefit from more energy and goods than ever. We have instant access to more knowledge today than everything until the 20th century. And actually, for most people here, online or in Israel, there is nothing really necessary that we cannot pay. Well, nothing but years of life. And we do not live much more longer than 2000 years ago. And the maximal lifespan of humans is even lower today than it was when Jean Calment died more than 20 years ago. And what many longevists do not know or forget is that there is also no real progression since many years for mice. To change this, one of the few ways is what is done by the Longevity Escape Velocity Foundation and by Aubrey de Grey. It is to progress for tests on mice. We need this, and all longevity specialists I know agree about the fact that the first phase of this experiment was successful, interesting, no problem. But we need a second phase and then other phases of this experiment. And for reasons I do not understand, really, I do not understand why, there is no money at the moment to start the second phase of the study. And that's why, like Aubrey said, that I gave 200,000 euro last month, and that during this month I will match all gifts until 200,000 euro also. So please help me to become poor and help to make research for longevity faster. The amount of money necessary is nothing compared to the cost of swords, and nothing compared to the cost of cosmetics, and nothing compared to the potential benefits for billions of people. That's all. Thank you for listening.
Well, thank you so much, Didier. And above all, thank you so much for your enormous generosity in helping this work to happen. There's no words to describe how important this is. So thank you so much. Okay, well, so now I'm going to try and share my screen, and let's see if I can find some slides. Here we go, share. I hope that's working. Let me just go to that mode. Okay, could somebody confirm that that's actually working and you can see my slides on the screen? So I'm just going to give a brief description of what we're doing at LEV Foundation and what we intend to do, as Didier mentioned. I know that most people in the audience are pretty familiar with my past work and how I look at aging and how I look at the options for doing anything about it. So I will just give a very brief background in that regard. I always start by highlighting this question, the paradoxical question, why the health problems of late life are so much more resistant to medical intervention than the health problems of early life that used to kill so many people, even in the wealthiest countries in the world, until the last century or so. And of course, the way that I look at this is as a problem of preventative maintenance. I think it's very important to recognize that since the human body is a machine, albeit a really complicated one, we should be able to extend its fully functioning longevity by the same kind of approach that we use to extend the fully functioning longevity of simple man-made machines like this one. The key thing here is this car is more than 100 years old, and it did not get that way by having been originally designed to last 100 years. Not at all. It was probably designed to last 10 years, but preventative maintenance has completely transcended that warranty period. So what that means in terms of medical intervention against aging in living organisms such as humans is this. We have a hugely complex network of processes that keep us alive from one day to the next. And that is what I'm calling here metabolism. That's the word that biologists use to describe that network. And then late in life, we have the pathologies of late life. The reason why the pathologies of late life are not something that happens throughout life is because there is this intermediate set of changes at the molecular and cellular level, which I'm calling damage. And those changes do occur throughout life, but the body is set up to tolerate a certain amount of them. So there is no functional consequence to speak of until middle age or older. And what this means is that our goal is to separate metabolism from pathology, to allow us to continue being alive without getting sick. And the approach that has dominated medical attempts to do this is what I'm calling geriatrics, which essentially ignores the damage that accumulates throughout life and tries to go after the pathologies directly as if they were infections. And lo and behold, it doesn't work at all, really. We've made hardly any progress in postponing those health problems, as Didier mentioned. Then we've got what I'm calling the gerontology approach, which a few people started to realize might be better even a century ago. And that's where the whole field of gerontology came from, inspired, of course, by the living world, in which we see a huge variation in different species in terms of how rapidly they age. But that has also been unsuccessful, essentially because the creation of damage is too inextricably intertwined with the things that we need metabolism to do to keep us alive. So the innovation that I introduced 24 years ago now was to say, well, okay, if these processes can't be attenuated, let us instead separate those processes from each other by doing preventative maintenance, which means going in and every so often removing some or most of the damage that metabolism is generating so that it does not reach the pathogenic threshold. And in specific terms, I enumerated way back then 7 major categories of aging damage. So this was the original hallmarks concept before hallmarks were cool. And I personally still think that it's a rather better description than any of the more upstart versions that have come along lately. Not least, it includes the stiffening of the extracellular matrix that Fiona mentioned a moment ago. And the point of this classification, which is somewhat missed, I believe, in the more recent hallmarks papers, is that each of these categories corresponds to a generic approach to actually doing the maintenance, actually restoring the molecular and cellular structure. Furthermore, progress has been made, a lot of progress in those 20-odd years. So first of all, I want to emphasize that there are now multiple different approaches to each of these things. If, for example, cell loss used to be only something that could be addressed using stem cell therapy, and now we have the concept of partial reprogramming, which essentially rejuvenates and increases the stemness of resident cells. And so we may not need to use stem cell therapy for everything anymore. The same is true across the board, across all of the other 6 categories. And furthermore, as again Fiona mentioned, this has now been able to progress into the private sector. So we are looking at startup companies, looking at all of these things, and that is very encouraging. But there are some problems when we think about how to translate this to the clinic. Yes, there are great opportunities. Damage repair seems to be the most promising way to go in terms of benefiting people who are already in middle age, and it will benefit people who are progressively older as treatments improve. Furthermore, there is a clear synergy with the longevity treatments that are more in the way of the gerontology approach, as I called it earlier, things like calorie restriction mimetics. So, this is all good news. But there are challenges. The first thing is that this damage repair approach is inherently a divide and conquer approach, such that one needs to do multiple different things to the same individual at the same time. And those things are inherently hard to interpret and thus to refine. A huge problem that we also have is that across the whole world, we have regulatory structures for approval of medical treatments that have been designed and optimized for pharmaceuticals. And they are really not fit for purpose when we think about gene therapies and cell therapies, which is absolutely going to be necessary for this. Furthermore, they're really not built for combination therapies. And so this, needs to be modernized. And unfortunately, there's another problem, which is slowing down the pressure to modernize regulatory structures. And that is that the public are inherently suspicious of preventative medicine. Of course, this is only preventative medicine in the sense that it's designed for people who are not yet sick. It is, of course, also a treatment in the sense that it genuinely eliminates damage that's already occurred in the body. But, the fact that people are not yet sick is kind of the point from the point of view of the public. The public, who are very bad at reasoning about uncertainty, tend to be worried more about the possibility that some new medicine might accidentally make them sick, rather than the fact that it might delay how soon they get sick. So what are we doing about that at LEV Foundation? Well, we're not working on humans, we're only working on mice. And of course, we know all the problems that, that exist for translating mouse work to the clinic. But first of all, we feel that translation is likely to have a higher hit rate for damage repair interventions than for pharmaceuticals. And indeed, the interactions between those damage repair interventions should be more predictable. Both of these things we feel simply because damage repair is not trying to interfere with metabolism. It's leaving metabolism alone and just interfering with changes that are essentially inert initially and are not participating in metabolism. So I'm going to talk about the study we're doing, the robust mouse rejuvenation study, and in particular, the first iteration of it, which has been happening since early last year, and it's nearly complete. And then I'll also talk about what we want to do in the future. So I've told you a few things about the problems, the challenges that are faced here. Another challenge that's really important is that combining things that already exist and that are owned by other people, if they're patentable at all, it doesn't generate significant new intellectual property. So it's hard to make it attractive to investors. Moreover, it's hard to make it attractive to academics because we're not really testing hypotheses, we're not really exploring mechanisms of action. So we've got to do this, but it's hard. It's hard to get funding for it. A huge part of the reason why we have to do it, though, is that it may be able to break down the public skepticism and ambivalence that I mentioned a moment ago. If we can do really powerful extension of lifespan in mice, then it will make it difficult to believe that we'll never do it for humans, even if there may be differences in the actual intervention. And so what we mean by a dramatic improvement is we want to add a whole year to the lifespan of normal mice using these interventions. Now, of course, that can already be done with calorie restriction, but only if you start early in life. If you start in middle age, so what I mean by that is around 1.5 years old for mice that normally live to about 2.5, then the most that anyone's ever achieved is about 4 months. So we want to treble that. We want to get 3 times as much effect as anyone's got before. And we believe that if we can do that, that will be, the AlphaFold moment, the moment when people really get that this new approach of damage repair can be very much more powerful than anything we've tried in the past. So that's what we're doing. We're starting with middle-aged normal mice, and we're trying to extend their lifespan. And the question then, of course, is how do we choose which interventions to combine? So I'll get to that in a moment. But first of all, I want to emphasize that when you're doing a study with a lot of interventions, in our case, 4 interventions, then it's a really big study because you don't just have a treatment group and a control group. You also have to have partial treatments. So what we have here is, of course, a control group that's not getting these things, and also a treatment group that's getting all 4 things. But we also have to make sure that we're doing the experiment correctly. We have to validate our interventions. So we have to have groups that are getting only one of the interventions individually. And we also want to identify those antagonistic interactions where interventions might cancel each other out. And so that's why we have groups getting all but one of the interventions. So that's 10 treatment groups, which means we are looking at 1,000 mice, 500 male, 500 female. And I apologize for the tannoy. I'll wait for a moment. Really good. So you can see on the left, we are doing all manner of health span measures as well as lifespan. We're doing visual things like alopecia and kyphosis. We're doing behavioral things, memory, deafness, blindness, grip strength, endurance. We're doing blood tests, doing a whole bunch of tests on things like glucose tolerance. And of course, we're sacrificing mice every so often and collecting tissues, including from the mice that die naturally, so that we can analyze them in ways that are more informative than non-invasive interventions. So yeah, as I say, it's a huge study. And that, of course, is why it costs so much. It cost $3.5 million, this study, and most of that money had to be found at the beginning because most of the interventions are done and the labor happens at the beginning. So here is what the things we're doing. We have one intervention that is not damage repair per se. It's a calorie restriction mimetic. Wait a second. And of course, that's rapamycin, the most effective calorie restriction mimetic that we have at the moment. We're giving rapamycin throughout the lifespan, starting at 18 months. So very similar to experiments that indeed began the whole rapamycin craze back from the interventions testing program more than a decade ago. We're also giving young bone marrow stem cells. So, of course, there's a huge amount of emphasis at the moment on plasma, on young plasma for old mice. Seems to be helpful, but we think the cellular component needs to be addressed as well. People have shown that if you do heterochronic bone marrow transplant, you get very substantial increase in lifespan. So we wanted to include that. Similarly, for telomerase gene therapy, which has been shown by Maria Blasco's group and others now to extend lifespan when started late in life. And finally, a senolytic, navitoclax, which we are administering in its prodrug form with conjugated to galactose, which reduces its toxicity. And so I've said all that already. And here are the results as they currently stand. You can see that the survival curves are not complete because the experiment is still ongoing. But we are definitely learning a lot from this. If you look at the 2 sexes, you can see quite significant differences. Let me focus you on the thick lines, the thick blue line and the thick red line, because those are the thick red line, of course, is the group getting all the interventions, and the blue line is getting none of them. And it's nice and clean in the females. The thick red line is better than all of the others, and the blue line is worse. And all the others, of course, are these 1 treatment or 3 treatment. And you can see that there is, nice additivity. Of course, different interventions are contributing different amounts, and there'll be a huge amount of analysis once the study is complete, when we can do the statistics properly to get, to figure out what we can most confidently say. In the males, the story is a good deal more complicated. You can see that a couple of the treatment groups were actually doing worse than the controls for a while, though those ones have caught up, while other ones that were doing better have actually fallen away. But this is the kind of thing that one's going to expect in a big study like this, with lots of different hypotheses being tested all at the same time. The main point here, however, the main takeaway is we feel that this has very robustly validated the concept that we are pursuing here. We definitely are not getting a whole year of life extension. In fact, we are, right on the cusp of beating that 4-month life extension that I spoke about earlier, but we won't beat it by all that much. So one thing that we definitely are considering, subject, of course, to funding, is including more than 4 interventions next time. Let me talk a little bit about what we're hoping to do. One thing that we absolutely want to remember and never forget is that the same interventions that we're doing now may work better at different doses. The stem cells in particular for the bone marrow, we had to compromise relative to the published study from other groups because of cost. And we could have given them more stem cells if we had more budget. But the point is, we do desperately need to do more of these studies. Our first design for a follow-up study is described at the URL right in the center of your screen in green, levf.org/RMR2. That has been up and publicly available for nearly a year now, and we would have dearly loved to have begun it, at least 6 months ago. We believe that the study is an improvement on the one that we've just done and has a better chance of getting a very substantial increase in lifespan. And we are continuing to refine these designs of new studies while we try desperately to put together the funding to actually do them. I'll stop there. I'll just emphasize that my email address is public and it's always available. You can always write to me. I'm very well behaved with email. And of course, I want to thank our donors, without whom nothing could have happened at all, as well as our team at ICOR Life Sciences that have been performing the work, and our collaborators and advisors. For those of you who want to dig deeper into the science and justification and motivation of all of this, please have a look at the review paper that we published 6 months or so ago, which the URL is right there. And finally, again, I want to emphasize that anyone who feels they may be able to help financially, you will be saving a lot of lives if you do in the future. So there is the QR code for our donate page and also the URL itself at the bottom. Thank you very much.
Thank you, Aubrey. Thank you very much. Any questions from the audience? People who are still here, who still, keeping strong for longevity? Please, but ask in English.
Shalom, Audrey. When are you coming to Israel?
I don't know, to be honest, but of course I've been to Israel a few times before, invited indeed by Ilya, so I'm sure I'll be back.
Indeed, Aubrey was here as far away as 2013 and 2014 in the conferences we organized. One of the first longevity conferences in the world, specifically addressing aging as a medical condition. That's Aubrey's words, your words. I hope I'm not distorting anything. And we hope to see you in Longevity Nation 25 when the planes fly and and there are no rockets anywhere.
So just a technical question. So how old are the oldest mice still alive? And maybe there is still a chance that you beat, the limit by quite a lot if there are some living mice, remember?
Sure. Yeah, the oldest mice as of now are about 3¼ years old, so about 39 months. And we've got about 20 mice left of the original 1,000 mice. So yeah, I don't know whether we're going to beat any records for individual lifespan, but it's going to be very close. And of course, we're looking at that. We're also looking at average lifespan, and we're also looking at, the usual measure of maximum lifespan, which is the age of the top 10% of mice. So yeah, we hope so. We don't know yet.
Aubrey, do you see some questions in the chat that you want to answer? If you have the ability to see them.
I do, but there's not actually much in the chat, but I do see a couple of hands up. Didier and Fiona have got their hands up.
Yeah, actually, you can have their questions. They can just speak. Their co-hosts, so they can speak and just ask them directly. Welcome, Didier, Fiona.
Yes. Two questions to you, Aubrey. The first one is, do you know if there are other organizations who are trying to do kind of the same as you are doing, copying you? And the second one is maybe there is one thing for me important. It's that the experiments normally for mice should be blind, that the people, let's say, caring for the mice do not know if they are treated or not. And I think it was not really the case for the first phase. So are you taking some measures that, yeah, of course, it's probably not possible to be perfect, but at least that the people caring for the mice do not know about which mice are treated or not. That's all.
Yeah. So for the first question, there are other groups. There seems to be a general consensus, as you mentioned, that these are valuable experiments that need to be done. But at the moment, the closest that we are at is combination experiments in which the only things that are being used are orally available things. So, of course, we've got one orally available thing, rapamycin. People are trying it with acarbose. People are trying metformin as well. Various combinations. Brian Kennedy, in particular, is doing quite a bit of this, but only with orally available interventions, not with anything that needs to be injected. And we believe that that's a fatal limitation. That you're really there's going to be a hard wall beyond which you're never going to get, unless you do cell therapies and gene therapies as well as things that can be supplied in the chow. As regards blinding, yes. So of course, some things blinding is more important than for other things. So, for example, you don't have to worry about people knowing whether which treatment group a particular mouse comes from in order to measure its lifespan. That's something that doesn't need blinding. And that's true for many of the other interventions, the ones that are just, measuring body weight, for example, or things that are clearly quantitative and objective. The time when blinding is more important are cases where you're measuring things in where there is the possibility of observer bias. And those things tend to be the experiments that we haven't done yet. So, as I mentioned, we've stored a lot of tissues, both fixed and frozen, and we are actively seeking collaborators to analyze those tissues. There, it certainly will make sense to do, at least in some cases, to do the analysis blinded, but we can certainly still do that. We have not in any way lost the ability because we will be giving the tissues to other people. So, we're not too worried about that. Now, you do make a good point in the chat, though, Didier, that the mice may actually the technicians may somehow try harder to keep the treated mice alive rather than the untreated mice. But that's something one can very clearly, train technicians not to do. And the people that are working on this at ICOR have got a lot of experience of this, so I'm very confident that that won't have happened. It is a good point, though. There's a famous case during the Wisconsin calorie restriction study on monkeys that happened some years ago now, in which one technician did start feeling sorry for the calorie restricted monkeys, and started giving them more food than they were supposed to have. And that was picked up eventually.
Thank you. Thank you, Aubrey. And the last question from Fiona.
Hi, and just for the record, I'm Robert Cargill. I'm here with Fiona. So, hi, Aubrey. Very nice presentation as usual. I had a couple of points. The first one was I'm very happy to see that you're including activity as part of RMR2, and I was hoping to hear a little bit more about how that's going to be distributed across the groups. I think that one of the really concerning confounds of the vast majority of mouse research that's been done to date is that it's been done on animals that are basically bored and fat because they're stuck in a cage and have nothing to do but eat. So first, if you can give us a little more detail on what you're planning there. And then the other confound that I see that drives me crazy is that we're doing all this work in animals that face no immune challenges, which is completely unrealistic considering that a tremendous amount of disease and death in humanity is due to infectious diseases. So can you address whether or not there's any hope of getting some sort of controlled immune challenges into our longevity work? Thank you.
Sure. Okay. So for the first question, yeah, the way we've decided to do this, precisely because, as you say, exercise is very well established as an important thing to keep mice happy for longer. We're just going to give all the mice exercise. The way we're going to do it, we've just put running wheels in the cages. We may, depending on what on the logistics, we may actually put 2 running wheels in each cage so as to avoid any effect of dominance, because of course we've got multiple mice in each cage. And we're actually going to do the same thing for rapamycin, because again, it's really proven to work. So we're just going to give everyone rapamycin next time round. And the 4 things that, or more, the things that we're testing, with half the mice getting them and half not, will be additional things on top of those. As regards to the immune challenge, yes, I mean, you're quite right. It's incredibly difficult to do. I mean, otherwise it would be done, right? Because of course, what you've got to do is somehow standardize the immune challenge, and that means that the thing you're giving, the mice all have to get the same dose of the infection, things like that. Honestly, I think that at the moment that's probably likely to do more harm than good to interpretation of this experiment. But I'm very much open to input from immunologists. Of course, we talk to immunologists a lot with regard to any ideas that might be able to make that kind of thing work. I do agree with you that it is a confounder that's quite problematic.